Test, test, test. Hey everyone, how's it going? This is your teacher, Mr. Brewer. Doing some video recordings for the very last packet going out. Hope you guys have been okay during this time. I hope these videos have helped you out in some small way. That's the least I can do to help you guys succeed. If you've been watching the videos all this time, and you've been using them to help you out with your packets, then you should have no problem being prepared for next year, and also no problem graduating, or not graduating, sorry. Some of you are graduating, yeah, but passing this class. So this is the last 4 sections of the packet material. This time I did it a little bit different. I just printed out the entire lesson out of the book. That way there's nothing for you to fill in. I will be talking about it though. So you can skip these first videos titled lesson if you would like, just to read the portion of the packet and then attempt the exercises. I'm still going to have those tutorial videos for the exercises. So for right now, let's get into this lesson here on proving triangles similar. So the first thing is the investigation. It says draw 2 triangles of different sizes, each with a 50-degree angle and a 60-degree angle. So we have triangle ABC and triangle DEF. They have different side lengths with the same angles. This says measure the sides of each triangle to the nearest millimeter, and then find the ratio of the lengths of each pair of corresponding sides. So find the ratio of AC to DF, the ratio of CB to FE, and the ratio of AB to DE. And what conclusion can you make about the 2 triangles? Well, when you do this, you'll find that the ratio for each corresponding side is the same. So remember, to prove triangles are similar, we need 2 things. We need to know if their angles are the same, and then we need to know if they have the same ratio for each side. We call that the similarity ratio. So if these shapes, not necessarily just triangles, any shape, if these shapes have the same vertices, the measure of the vertex, and the same similarity ratio, then they are similar. So this conjecture here, if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are, this is going to be similar, then the 2 triangles are similar. And this basically spells out the angle-angle similarity postulate, which says if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. So they're similar. So meaning they're not congruent, they're not exactly the same, but they are similar in that this triangle is a fraction. The side lengths of this triangle are a fraction of the side lengths of this triangle. So go ahead and flip the page. So we have our first example here, using the AA postulate, AA similarity postulate. Explain why the triangles are similar, write a similarity statement. Angle RSW is here, and VSB are vertical angles, so they're congruent. So these guys are congruent. Angle R is congruent to angle V because their measures are equal, they're both 45 degrees. Therefore, triangle RSW is similar to triangle VSB by the angle-angle similarity postulate. So I'm going to go over these check understandings here just to give more basis about these lessons. So in example 1, you have enough information to write a similarity statement. Do you have enough information to find the similarity ratio? Explain. So remember that on the previous page we found the similarity ratio because we were able to measure the sides and compare the sides, the corresponding sides to each. And to do that we had the lengths of each side. So because I don't have the lengths of each side, I can say that no, because I don't have the side lengths. Corresponding side lengths. I don't have enough info to find the similarity ratio. Okay, so the next two theorems follow from the AA similarity postulate. The next one, side angle side. If an angle of one triangle is congruent to an angle of a second triangle, so here we have two triangles, angle A is congruent to angle Q, and the sides including the two angles are proportional. So the sides including the two angles, remember including means in between. So this side here and this side, and this side and this side, if they're proportional, then the triangles are similar. So they walk through the proof of it. You're given that angles are congruent, the sides are proportional. You want to prove that ABC is similar to QRS. It says choose some point X on QR so that QX is equal to AB. So they did that here. See figure at left. Draw line XY and RS, they're parallel to each other. Then angle QXY is here, is equal to angle R. Okay, that's true because they're corresponding angles. By the angle-angle similarity postulate, triangle QXY, so QXY, this small triangle, is similar to QRS. Okay, because we have two angles and corresponding sides. Thus, QX, so this side here, is proportional to QR, and QY is proportional to QS. Combining this proportion, the given proportion, and the fact that AB is this side, is equal to QX, shows that the ratio of AC over QS, so AC is here and QS is here, is equal to the ratio of QY to QS. Hence, AC is equal to QY. Then triangle ABC is congruent to triangle QXY by side angle side congruence postulate. So we have side angle and we have side angle side. Okay, it's because this angle is the same. Angle B is equal to angle QXY by the corresponding parts of congruent triangles are corresponding parts of congruent triangles are congruent. And angle B is congruent to angle R. Angle B here is congruent to angle R by the transitive property. Thus, triangle ABC, this triangle, is similar to triangle QRS by the angle-angle similarity postulate. That was a long proof. What do you think? So, unless you love spending hours trying to understand this, sometimes it's okay to take the textbook for what it's worth and then go back later to understand it better by looking at the proof. Because proofs do take a long time to come up with. And it's not until much later in mathematics or life that you'll be challenged to create proofs for things. And hopefully you'll be making lots of money by then. If the corresponding sides of two triangles are proportional, then the triangles are similar. Okay, that's the side similarity theorem. So here's another proof. How about I spare you guys my voice and we'll move on here. So example 2, using similarity theorems. Explain why the triangles must be similar. Write a similarity statement. So here we have two triangles. Angle QRP, which is here, is equal to XYZ because they're both right angles. Side QR is corresponding to QY, and the ratio is 3/4, so 3/4. And then side PR corresponds to side ZY, so it's a 6:8 ratio, which also equals 3/4. Therefore, triangle QRP is congruent to triangle XYZ by the side angle side similarity theorem. Okay, so notice we're not trying to find congruent sides here. That would be finding congruent triangles. that would just be the side angle side theorem. This is side angle side similarity because these sides here are corresponding, meaning they have the same ratio. So this is a 3/4, and this is also a 3/4 if you reduce it. Check understanding. Explain why the triangles must be similar. Write a similarity statement. So ABC, and then we have GEF. Okay, so I don't have any angles. However, I do have 3 sides. So I'm going to try and use the side similarity theorem. So let's do this triangle is upside down. So let me just redraw this so they look the same. So I'm going to rotate this one 180 degrees. So that puts AB down here. Yeah, these are the same side. And then C is the top, 6, 6, and 8. So let's say E, and I'm gonna go small to big. So I'm gonna say side AC corresponds to side EG, and that's a 6:8 ratio. And then I'll say side CB corresponds to side GF, and that's also a 6:8 ratio. And then side AB corresponds to side EF. That's an 8:12 ratio. Oh, I'm sorry, not 8. That's a 9. Hello. That's a 9:12 ratio. Okay, so let's reduce these. 6/8 is the same as 3/4. If you don't believe me, put it in your calculator. This is 3/4, and then 9/12 is also 3/4. All I did is I pulled out 3s. This is 3 times 3, and this is 3 times 4. I'll show you guys something. 9/12, right, is equal to 3 times 3 over 3 times 4. Well, I have a 3/3 that becomes 1. So this is 3/4. 6/8 is equal to 3 times 2 over 4 times 2. 2/2 cancels, that becomes 1. It's 3/4. Okay, so since these all have the same ratio, then they are similar. So I can say triangle ABC is similar to triangle EFG. And the similarity ratio is 3/4. So 3 parts small triangle, 4 parts big triangle. All right, let's get into objective 2. You can apply the angle-angle similarity postulate and the side-angle-side and side-side-side similarity theorems to find the lengths of sides in similar triangles. So let's look at example number 3 here. Explain why the triangles are similar. Write a similarity statement. Then find the length of DE. So right here I have a vertical angle, right? So it says ABC is congruent to EBD because they're vertical angles. So I've got one angle. So if I have these 3, if I have angle-angle similarity postulate, angle-side angle postulate, was it ASA? I apologize, it was SAS. And I have side, side, side. Which of these uses just one angle? It's side, angle, side. So let's go ahead and use that. So we're going to need, we have our angle. It's this central vertical angle. That means that I need to know if these two sides, CB and BD, are corresponding. They have the same ratio. And if AB and BE have the same ratio. So AB over BE is 12 to 18. That's equal to 2/3. And CB over BD is 16 over 24. That's equal to 2/3. So since these two, this side and this side and this side and this side, have the same ratio, then I'm looking at side angle side similarity. Let's see, what else did they do? Oh, and we have to solve for DE. Okay. Okay, so this smaller triangle obviously is 2/3 of the bigger triangle. So 10, they did 10 over DE, okay, is equal to 2 over 3. So that's going to equal, we cross multiply, that's 30 equals DE divided by times 2, divide this by 2, DE equals 15. Another way to do this is that you know that this triangle is 2/3 of this triangle. So if I simply multiply by 1.5, I'll reach 1. You can try it in your calculator. Do 2/3 times 1.5. You'll get 1. It's the same as doing this. 2/3 times 3/2. That's 6 over 6. That's 1. So you want to make these, basically what you're doing is multiplying this by something to get, you want the ratios to equal 1, basically. So multiply this by 3/2 and you'll get DE. So 10 times 3/2 is 15. I don't know if that made any sense. Yeah, you can continue to use this cross multiplying stuff, or you can, you just need to play around with stuff, okay? Play around with it. Whatever you get, just check it, okay? Is 10 2/3 of 15? Yes. If you get something else, say you get 12 over here, then 10 must be 2/3 of whatever this is, okay? If it's not correct, then you're off. Okay, next one. Find the value of x and then figure it right. So I've got two angles here. So I'm going to use the angle similarity postulate. So first I need to find if the triangles are similar, which they are because I had two of the same angles. Let's see here. So look at, see this double arc here, this double arc angle is across from the 12, and this double arc is across from the 8. That means that these are corresponding sides. So it's a 2/3 ratio. So it's just same as this one up here. That means that this small triangle is 2/3 of this one, or this big one is 3/2. Take the fraction and flip it upside down. This big one is 3/2 of this. So what you can do is you can do your cross multiplying. You can do 6 over the hidden angle is equal to 2 over 3, right? And then you can cross multiply and you'll get an answer. Or you can do 6 times 3/2. X equals 9. Try it. Pause the video and try it. Okay, moving on. You can use similar triangles and measurements to find distances that are difficult to measure directly. This is called indirect measurement. One method of this uses the fact that light reflects off a mirror at the same angle at which it hits the mirror. A second method uses the similar triangles that are formed by certain figures and their shadows. Go ahead and flip the page. Okay, geology. Ramon places a mirror on the ground 40.5 feet from the base of a geyser. So here's the geyser. He puts the mirror down there. He walks backwards until he can see the top of the geyser in the middle of the mirror. He's a smart guy. At that point, Ramon's eyes are 6 feet above the ground, and he is 7 feet from the image in the mirror. Use similar triangles to find the height of the geyser. So this light here, okay, he's looking down, and that's the light he's seeing the mirror. This light is bouncing off the mirror. This angle here, it's hard to see, but this angle is the same as this angle. Okay, so let's see, so these are similar angles. What else do we know is similar? He's standing straight up right here. This is a right angle, and this is also a right angle. So I have two similar angles, so I'm going to use the angle-angle similarity postulate. So these are similar triangles. That means that the ratio of 7 to 40.5 is the same as the ratio of 6 to x. So all we need to do is find out what the ratio is. They do the cross multiplying trick. You can do that, or you can do 40.5 over 7 equals something. Open up a calculator. Ooh, that's a weird number. 5.785, etc., etc. Let's see if it's nicer going the other way. 7 divided by 40.5. Oh, that's even worse. Okay, that's all right. We'll just work with that. So we're going to do 40.5 divided by 7. This equals 5.7857. And it goes on. Okay, so that means that this triangle is 5.7857 times bigger than this triangle. So all I need to do is multiply 6 by this number to get this height. This is totally different than the cross multiplying trick, so just bear that in mind. I'm doing different things. I'm finding the similarity ratio, and then I'm going to multiply Ramon's height by that similarity ratio. So let's do this times 6 right here. $34.71. And they left it with one digit. I'm assuming that's because they gave you just one decimal place. Okay. So let's do a different one. In sunlight, a cactus casts a 9-foot shadow. So here's a 9-foot shadow. At the same time, a person 6 feet tall casts a 4-foot shadow. Use similar triangles to find the height. So here we have similar triangles. So use similar triangles. Okay, so this is by side angle side, since we only have. Well, I take that back. This angle is actually the same because the sun is hitting the person and the cactus at the same angle if they're right next to each other, assuming they're next to each other. So these are similar. So we can do the same way as up here, 9 divided by 4. That's going to be a 2.25. So that means that the cactus is 2.25 times bigger than the person. So that's going to be 1.5, 13.5 feet. 13.5 feet tall. That's how tall the cactus is. Okay. Well, let me set it up the cross multiplying way in case you like that way. Let's do it that way. So 4 is similar to 9, as 6 is similar to x. Right? So let's cross multiply 24x. Oops. 4x equals 54. And then do 54 divided by 4. You should get 13.5. Okay. I'm going to stop this video, and then we'll do the tutorials in the next video. Alright guys, see ya.